Algebra 1, Common Core, Unit 3, Section 4, Factoring by Grouping. So the three videos before this covered the three basic factoring styles that you've learned are greatest common factoring. That's where you look to see that everything in the polynomial has something in common which you can then divide everything by. Then you learned about difference of two squares factoring. And that's where you had a binomial, a subtraction in between two terms. A difference of two squares. The square terms, the numbers had to be squares, the exponents had to be even. And then the last video learned about trinomial factoring. And that's, where there's three terms, and we go back a page, you see there's three terms here. There's an A term, a B term, a C term. It's what multiplies to that constant adds to that middle term. And so that, the trinomials is probably the most complicated of these. Because the GCF is really just division, and dots is a pretty easy pattern once you see it. But you have to be able to recognize the different types of factoring. GCF is there's something in common. The dots is two terms, subtraction sign in the middle, square numbers, even exponents. And the trinomials are three terms. And again, we've talked about how the last video, that was basic trinomials where there was, no number in front of x squared except for that invisible 1. But we will eventually see more advanced trinomials in 3.5, advanced trinomials. But now, before we get to that, we want to do something called factor by grouping. And factor by grouping is actually very easy to recognize because primarily it's going to be when you have four terms. So we know like dots is when you have two terms, trinomials is when you have three terms. Well, factor by grouping is four terms. It is possible to actually do it with 6 terms and 8 terms, but we're not really going to get that advanced in this course. So it's pretty much when you see 4 terms, you always want to start with the GCF. Is there anything in common with all 4 terms? If not, then you're going to do what's called factor by grouping. And when we do get to video 3.5, advanced trinomials, one of the things is we take the trinomials and we expand it to 4 terms and then do factor by grouping. So first we got to learn factor by grouping before we get there. So anyways, 4 terms. Factor by grouping is a method that groups terms in a polynomial into 2 smaller groups and uses GCF. So we're actually going to do some GCF factoring in the factor by grouping process. See, what you do is when you have your 4 terms, the first group, all you do is you draw a line right down the middle. You cut it in half. And you make it 2 terms on the left and 2 terms on the right. And then you factor each side using GCF. So take a look at, what we have here. X to the third minus 5x squared. What do they have in common? They have x in common. And not only that, we could take out x squared because this one has 3 of them and this one has 2 of them. So we could take out 2, x squared. That's what I mean by 2. So what's left over? What's left over when I take x squared away from x to the third? When I divide x to the third by x squared, I'm left with just x, which is like x to the first. And when I divide negative 5x squared by x squared, I'm left with negative 5, right? There's 2 x's in there, and I'm taking away 2, so there's none left, just the coefficient, negative 5. On the right side, I'm also doing GCF factoring. And it's actually very common on the left side to get a variable GCF, and on the right side, you should get a numerical GCF because your constant on the end typically won't have an x. So we can't take out any x, so it's what number can I divide them both by? And in this case, it's negative 4. And a good tip here is whatever the sign is of the first thing, you want to take out something with that sign. So you see that, this right side starts with a negative, so I'm taking out a negative, and it happens to be negative 4. When I divide negative 4 from this, I'm left with x. Divide negative 4 from 20, I'm left with negative 5. So you split it in half, and then you really kind of do GCF here, GCF here. So we are doing GCF factoring. Then after you do GCF factoring, you continue to group a little bit. What you do is you then set it up as the double parenthesis we're very familiar with from the dots and the trinomials. And what goes in these is you take the GCF from both groups. So you combine the GCF I took from the first group and the GCF I took in the second group, and you put that into one of your parentheses. And then what you may have noticed here already is, what was left over when we took out x squared was x minus 5. Well, what was left over when we took out negative 4 was also x minus 5. This is what's referred to as the common quotient. And that's not a coincidence. That actually happens every time. If you don't get the same thing when you take out the GCFs, if you don't end up with a common quotient, then something's wrong and you're making a mistake. So it's kind of nice that there's actually a built-in check into the method as you go. And so that common quotient goes in one of your binomials. And then your two GCFs combine to go in the other set of parentheses. And so that's factor by grouping. But then we're still not done. Sometimes we're done, but you have to take a second look at this, especially the term that has the x squared. It is often a dots. And in this case, it is. X squared minus 4 factors to x plus 2x minus 2. The x minus 5 is still just x minus 5. So a lot of times when you're factor by grouping, you'll end up with 3 sets of parentheses. There are going to be cases where this x squared term cannot be factored. Like if it's x squared plus 4, you can't factor it, and then you're done right there. If it was x squared minus 7, again, it's not a square, can't factor it, you're done right there. So there are times where this is as far as it goes, but if this works out to be a dots, which it often does, you got to keep going, and you end up with 3 things. Let's do a couple fresh examples, right? So I see the 4 terms, just going to slice it right down the middle, and taking a look at the left side, what can we take out? Let me zoom in a little bit. So on the left side, again, on the left side, there's always at least an x GCF here. But again, look at I have x to the third and x to the second, so I could take out x to the second. You could take out the lowest exponent between what they have. What's left over? When I take x squared away from x to the third, I'm left with just x to the first. When I take it away from, sorry, let me try to get that box out of there. There we go. When I take x squared away from 2x squared, I'm left with the plus 2, right? And so you got to be good at doing GCF factoring because that's a large part of this. Now on the right side, I have negative 9x minus 18. Again, because this starts with a negative, I want to take out negative something. And both these numbers can be divided by negative 9. A lot of times it is that number. Not always, but a lot of times it is. And then what's left over when I take negative 9 away from negative? Remember, negative divided by negative is going to be positive. And what's left is that positive x. And then that negative 18 divided by negative 9 is positive 2. And now I know things are going well when I end up with the same thing in those parentheses. So now I'm ready to write the double parentheses. I group the 2 GCFs. So x squared minus 9. And then I write the common quotient. So now I got 2 of these, but I combine those to be written just once. Just like I combine these to be written just once. Don't think you write x plus 2, x plus 2. You don't. Right, you only write it once. Actually, what's really happening, but a lot of students have trouble seeing it, and I hesitate to even mention it, is at this phase, what you're doing is you're factoring out the x plus 2. And then what's left over when you take x plus 2 away from each of these things is you're left with x squared minus 9. But if you don't see that, that's okay. That's, a lot of students don't. It's just important that you know that you combine your GCFs and then you have your, common quotient. Then you really need to take a look at the term with x squared. Can it be factored again? Is it a dot? In this case, yes, it is. X plus 3, x minus 3, and the x plus 2 stays what it is. Now, if you ever find yourself with 4 things, then you probably did something wrong. Now, whatever your highest exponent is in the problem, in this case, the highest exponent in the original problem is 3, that means that's at most you can have 3 factors. You cannot have more factors than your highest exponent. So if your highest exponent is 3, you can't have 4 parenthesis sets. Okay, just keep that in mind. All right, let's try another one over on the right side. So again, I just slice it in half. Again, I could take out x squared, and I'm going to be left with x minus 5. On the right side, I see the negative I'm going to take out. It's going to be a negative 4. And again, I'm left with x minus 5, so my common quotient. Combine those 2 greatest common factors into a pair of x squared minus 4 and bring down the common quotient. Is it a dot? Yes, it is. It factors to x plus 2, x minus 2, and x minus 5 gets brought down. Done. 2 more. First with the left. Cut it in half. Take out x squared. Left over is going to be x minus 3. Pretty terrible 3. There we go. Still sloppy, but that's okay. Take out, this time it's a plus, so taking out a positive 4, left with x minus 3. Common quotient, so I know I'm good so far. Combine the GCFs, x squared and positive 4, and x minus 3. Take a second look at the x squared. Can this be factored further? No. Now, the previous problem was x squared minus 4. That is a dots. It is a difference of two squares. Remember, difference of two squares has to be subtraction. Has to be square number, even exponents, subtraction. So this one has the even exponent, has the square number 4, but the problem is it does not have subtraction. This would be a sum of two squares, which is not factorable. This is as far as it goes. So sometimes you'll get the dots that goes to 3. Sometimes you get something that's not dots, and it stays like that form. So you got to be careful. All right, one more final example for us, and then we're done. We're about 11 minutes. So let's see. Slice it in half. This one's a little more bigger numbers here, but the common factor is actually not just going to be x squared. Yes, there's x squared, but I could also take out a 4 from both 8 and 12. That's going to leave me with 2x plus 3. On the right side, now this happens sometimes. Notice that it seems like there's nothing in common here. There certainly is no x, and there's really no great number I could divide them both by, but you do have to take out something. And we know that, here we could divide both those numbers by 4, we could divide both these numbers by 9, both these numbers by 4. Well, you could always take out a 1. And remember, we want to take out that sign, so I'm going to factor out a negative 1. And then when I divide this by negative 1, it's good because I want to end up with the same thing here. And when I divide these by negative 1, it changes their sign, and I get that common quotient. So if you ever see, on the right side, it doesn't look like there's a common factor, take out a 1 or a negative 1, and always take out that sign. So if that's a negative, take out a negative 1. If that's a positive, take out a positive 1. And remember, that's going to get grouped there. So this is, your GCFs together, 4x squared minus 1 and 2x plus 3. Is this a dot? Yes, it is. 4 is a square, 2 is an even exponent, we got the minus, and 1 is square too. So it's going to be 2x plus 1, 2x minus 1 from the dots, and then bring down the 2x plus 3. So we see a lot of times we do get the dots, but occasionally we don't, so don't make the assumption, especially if it's a plus sign. You should know that's as far as it's going. All right, guys, that's 3-4 factoring by grouping, and we'll be using this method when we get to 3-5 for the advanced trinomial factoring. See ya.